Today's topic is about final impulse response filters. And basically, I could show you something about the on the filters first on that nice kind of brief summary of what I have done in wow what this one is doing. Okay, it looks like I have a broken file. So that's not intentional. Let's try it again. Okay, next slide. Okay, that was funny. It was starting a Metropolia presentation, which is kind of funny. Okay. Anyways, haha. So filter fundamentals. Today we are talking about the filter fundamentals, and basically we have division based on a spectral response. So low pass, band stop, high pass, and then multiband filters. And then another categorization is about the if the filter is FIR or IIR filter. Okay, yeah, so that's a typical example of how the low pass filter parameters are actually defined. So the pass band is basically the area where the frequency range where the signal is passing without any the attenuation, and then the stop band is the higher attenuation area, and then the area in between of those two, pass band and stop band, is the transition band. Okay. The say on analog filters, it's quite usual that we are just defined at the -3 dB to point, but it can be also defined by some other the attenuation point. So if we have a filter which has ripple on passband, usually the level of ripple is actually defined as the cut-off frequency. So just a reminder that it's not always like that. So the stop band actually is defined by the point where after the attenuation is within the specifications. So basically this filter can fit, for example, that stop band, but also if the specification says that okay, 10 dB is enough, which wouldn't be, but anyways, then the stop band will start already here. So it's always the kind of the definition is on the designer's view. Okay, high pass, the same thing, but of course it looks opposite. And then band pass, well, the difference is that we have two cutoff frequencies, the lower cutoff frequency and the higher cutoff frequency. And then also we have two transition bands and two stop bands with, they might have different characteristics. For example, like here we have less attenuation on the left-hand side stop band than on the right-hand side stop band. Okay, so and then example of band stop filters. Well, same way. We have cutoff frequency on both this low pass part and high pass part. We have one stop band in the middle and two transition bands again. Of course, these transition bands can be different. Okay, I told you already about this passband ripple. So if that is defined as one of these the filter parameters, then that will set up the place for the where the passband cutoff frequency actually is. Okay. About the why we are using FIR filters, only one reason, or actually two reasons. FIR filter is always stable. You cannot make unstable filters with FIR. Simply, you cannot. It's impossible mathematically. Of course, you can mess up the code, but that's the other story. But another one is the linear phase response. All the IIR systems have the non-linearity on the phase response. But if you have the impulse response symmetric over the center point, either positive or negative symmetry, then it's guaranteed that FIR filter has linear phase response. Okay, so it can be used on, for example, data communication, the applications, or say data communication. Where else? Yeah, or some pulse measurements, since this does not distort the pulse shape. All the nonlinear phase phase response system would distort this pulse shape. Okay. Three methods. Impulse response truncation is kind of it's not really a design method. It's one way to start to think about what we are talking about. So let me draw that one a little bit on the whiteboard then. So this truncation method basically just means that we have a system, or it could be a linear system, or on a continuous time space, and you then run the step function from function generator, and what comes out is the when you sample it, you get the step response, and actually then you get the impulse response from that one, and now you can simulate with some accuracy. You can simulate the system. So you have a copy of the system here. So instead of that one, you can make a kind of rough estimate on this system by putting here the h of z based on the impulse response you measured. This is very crude way and doesn't work that well, but it's quite simple to understand why it actually might work. Since, well, we need to figure out what is the transfer function on a black box. You don't know. Okay, one way is to actually evaluate whatever the system is by taking the step response on analog systems. Then you know that the impulse response is like that. Or, okay, how you actually could measure the impulse response of this room. That impulse you measure with the microphone, what was the response. Then you would have the copy of the room audio properties. Yes, it actually works. And that's how the professionals are measuring how they are setting up these big the audio systems on on big concerts. They are practically doing snap and measuring the spectral response and then tuning up the equipment based on that. I didn't know that, but now I have one of our multiform students, meaning evening students who has daytime job, and he actually told that okay, that's the reality how it's done. I was just what? There's some use for that theory. Okay, good. So back to business. There, windowing method. I go through the windowing method more thoroughly there on the whiteboard. And then third one, optimized design methods. Okay, windowing method is simple design flow, and it makes a lot of sense. The optimization, it requires a little bit more heavier mathematics, and there are actually tools already for it. On your MATLAB version, you can use FDA tool, for example. It has some of those optimized methods available there. Okay. And optimized meaning it calculates what is the optimal solution to have the least amount of calculations and still have the fitting the constraints of the design parameters. Okay. So next, yeah, I have some. Actually, I have done that one. I tried the analog low pass filter. Just made a small setup and measured with the those equipment. There is just a wave generator and oscilloscope and step function. As you can see, it's not ideal step function, but anyways, I got the step response and took that one to took that step response to MATLAB and started playing with it. So basically I got the now I can do the comparison between the model, analog model, directly the well, you're familiar with that formula, first degree low pass filter, and the corresponding the model system. Not too great, right? So you're hitting actually in a lot of troubles here. For example, one is the noise on your data. You have always noise on the data, so I have only about 25 dB signal to noise ratio. That's not even close to enough to actually get a good measurement of the this impulse response. Okay, and actually that one is a modeling of what happens if I didn't have any noise. Well, this is bound to fail because of in real world you always have those high spectral components, and then it means that if you are taking samples of that kind of system, you get the higher spectral components are showing up as the alias spectrum. Okay, so blue one tails up, while the green one is the real one that goes beyond forward and beyond to the infinity and back. Okay. So let's keep this one there. So windowing method. Those steps. Few steps to take to design an ideal low-pass filter. I will start with low pass and then just do some tricky transformations to get the high pass and band pass, band stop filters. But um, practically everything starts from the ideal case in continuous frequency space. An ideal case for low pass would be you have the or should I actually mark it F? Okay, I'll just mark it F. So frequency F, you have the cut-off frequency of Fc and of on the left-hand side minus Fc. Well, you have, and this would be ideal. You have a box-shaped filter, meaning that on the pass band it passes everything. Then on the stop band it attenuates everything. So nothing gets out on this frequency range, and everything gets out of the system on that one. So that's the ideal case. Okay. Next, what we can do. So this is the frequency space where we have the box. We can always Fourier transform or inverse Fourier transform that one to get the impulse response. Okay, so that one was actually the the amplitude response. And on ideal case, it has zero phase shift. So it's only real numbers. Well, of course, you can always mark it like that. But anyways, it's amplitude response model. Since we are only interested about the amplitude response at the beginning. And inverse Fourier transformation, the time space actually would give you a function you already know. That's our friend sinc. Sine x over x, or sinc function. I think the one definition is with pi, another definition is without pi. So we are engineers, we use pi. Okay, sine pi x divided by pi x looks like that. Okay, so that actually is h of t. So continuous time, the impulse response. But we cannot use the continuous time in digital systems. So what we can do there is to make the sampling. I try to make the sampling somewhat similar on both sides. That's why I'm doing it this way. Okay, let's sample it. So with a sampling rate of Ts is 1 over Fs, and we get a sampled sinc function, which is totally useless unless you cut it, since this is infinite impulse response function. So basically you need to cut it somehow, and mathematically this cut means that you will multiply the impulse response with a box. Another box. Good. So multiplying with this box will mark this 0, and now we are okay. This is now a finite impulse response system. So that h of n is actually that box, I'm actually, well, uh, this is my window at this point. So the windowing method, this is the window, the first window which we are using, Wn times the sink. Okay, I think it was, I can always go back and correct it, but I think this one was Fc over F, was Fn or Fs. We try with Fs and change if it wasn't. I never remember this one. Sink of N times Ts, so Fc divided by Fs. So this scaling factor here actually is needed for scaling this system to unity gain. I might have an error of 2 here, but we will see. Okay. Yeah, so N times Ts times Fc. I have a feeling that I have an error there, but we will see. Okay, so the next step is to test how close we actually got to the original design. So what we do for this impulse response, we'll do the Fourier transformation or calculate the amplitude response. To see how close we got. Fs over 2, Nyquist rate. But anyways, since we have this sink part here, it means that if you Fourier transform a sink, it actually comes the same way on the other side. So yes, we have something here going right. So we got the cutoff frequency set correctly with that one. So we get actually, if you do the Fourier transform of that one, actually what comes out is the Fourier transform of, okay, and then Fourier transform of some colors, the box, and then we have the sink, and okay, multiplication in time is same as convolution in space, in frequency. Okay, convolution. That's my marking for convolution. I think sometimes it's the dot inside of that box, and sometimes just this asterisk. But that means linear convolution. Okay, so this part here gives the box like it was on the beginning. It doesn't change anywhere. This one here, the Fourier transform of the box window would be sink in frequency space. And that one is the convolution. So when you convolute this one with this one here, basically you will have the, you know how the convolution works, right? So you have two signals, and you basically slide or multiply each of these values like that, and calculate the sum of those that product, and then you shift to next time shift and so on. So what happens here, due to the convolution, you will get actually a picture something like this. Although, okay, I'll just mark this one as the, if this one is the amplitude response of h, e, j, omega, then actually this is the absolute value. Okay, so having the box shape window will make the transition bandwidth wider or wide, and also it does not get all the attenuation because of the sink has, you know, every single frequency available from here to beyond. Okay, good. But that's the start. We can actually next go and try if we get a proper control over the cutoff frequency. Since, yes, with this method, compared to, for example, the running average, which is simple box window, we can actually control the cutoff frequency of the design. All right, let me take my octave here. Yeah, I haven't got any update on my MATLAB, unfortunately. So I will show this one on my octave then. So controlling cut off frequency FC with sync. So first things first, we need to start from somewhere. So we need to start basically by selecting, for example, 1, 2, 3, 4, from -4 to +4, the window width. Okay, so we have the indexes here n from -4 to 4 to sample that sync. Next, we need cutoff frequency and sample rate. I will start with the sample rate of 2000 Hertz and cutoff frequency of 500 Hertz. So basically this will be half band low pass filter. Right. So that's what I'm trying to do, or should I do it something? So that's about 1 kilohertz. Let me try to do this one. So that's roughly 350 hertz then. Yeah, I changed my mind. So this one is 350, just to make it, you know, look more like the what I draw it there. I have too many boundaries here. Okay, but we will see it. So 350. And now we can start sampling. Basically, the box function here, you have just 1, 1, 1, 1, 1 here. So you don't need to care about that one. What you need to care about with this box windowing practically is that you will just make the impulse response Fc divided by Fs. I have a feeling that this is not correct, but we will see it from the spec. So you have a factor of 2 mistake here. I'll probably get a low pass filter up here or low pass filter down here. We'll see. So sync n times Fc divided by Fs. There. And let me see that one. Frects of HH. One for FIR systems, just like making the delay. It's just the formula of yn equals to the convolution between this impulse response and the data. Okay, so the parameter A is now just scalar 1, 1024 points, and sample rate of Fs. And let's see what happens. Nothing. Strange. What's happening here? Ah, I got it. I think that I got the cutoff frequency on the wrong place now. Yeah, it's half what it should be, right? My cutoff frequency should be down there. So yes, it's not FC, it's Fn is the, so it also has too much of gain to there, I think, or is it? No, not necessarily. Let's try another time with better luck. So we define Nyquist frequency as Fs divided by 2. And calculate the HH again with the Fn in a hope to get the yes, looks better. In a hope to get the cutoff frequency on the right place. Sorry about that. I should remember it. But not the other, it's just factor of 2, engineering factor. Good. Nice. So we have a relatively flat passband, and we have a cutoff frequency at 350 Hertz, what I wanted. The only bad thing is about this ain't much better than any running average filter because of the stop band attenuation is not that great, only 20 dB. We can do much better stop band attenuation with the same number of same number of parameters. For example, I can take a triangular shape window. That will be easy to manage. So let me plot something now. So new plot and stem the current impulse response. So those were the weight factors to calculate that low pass filter. See, there are also negative values. And those are needed to shift the cutoff frequency on the right place. I can actually, for example, make a triangle window and see how this one would affect. So triangle window from -4 to 4 would be, here we have, let's see, 1, 2, 3, 4. So this is 1/4, 2, no, this is 1/5, 2/5. So triangle from here to here. Okay. 3/5, 4/5, and 5/5, yes, and then down. Uh, it also have a name. I think it was it Bartlett window? It's same as triangular window. But anyways, the idea here actually. Okay, let me jump back to the my whiteboard. Idea how to improve my frequency response from this one is to have a smoother window shape. Somehow smoother, since these edges give the trouble. You need very high spectral components with a relatively high power to produce that kind of shape. Remember this Fourier series, the box function Fourier series, right? Sine of omega t 1 over 3 times sine of 3 omega t, and so on. Was it like, I don't know, it's cosine. Anyways, so basically you have still on the say seventh harmonic still have quite a lot of energy on it. So basically the only way to start getting better the attenuation or stop band is to smooth the window somehow. Get rid of these sharp edges. And one way of getting rid of the sharp edge is the triangular window, which is very simple to produce. So, just a moment. Where should I click? Here. Good. So triangular window actually goes something like this. TR equals, all right, for, okay, 5 minus absolute value of n divided by 5. Yeah, that's triangular shape window. Now we can actually do the sync again. Let's see, but we already have the sync. Now we do use the other window, not this box window, but we use triangular window simply by selecting TR as the W function there and see what happens. There. So I'm just modifying the sync with the triangle shape window. There, and calculate the frequency response again. HHTR 1024 and FS. Oh, wow. Look at that. We get much more attenuation, 5 dB more. Yeah, I agree. It's not the greatest improvement in this human history, but anyways, it's a good start, and it actually shows a couple of points there. So the window shape actually made the attenuation go lower. Smoother the window is, meaning the less power on the high spectral components, then the more attenuation you have. It's kind of natural, since the most of the power of that of that smooth window is on low frequency components. But then actually it also means that our transition bandwidth now is wider. So it also the effects on the transition bandwidth. Okay, so now we can control cutoff frequency by FC and the stop band attenuation with a window shape. The next trick actually to do is the kind of last trick what we can possibly do here is to do something for the transition bandwidth that we just messed around. Okay, there we actually use the well-known fact that multiplication in time space is same as division in frequency space. Kind of, well, more or less straightforward. If you multiply time, you are then squeezing the frequency space. Yes. Wider here means narrower here. Okay. So that's the last point what we can do is to make this one wider. So we modify the width and see what happens here. I already know that it gets the transition bandwidth lower. But for that one, I would actually like to make a note that currently our transition bandwidth there, it's the cutoff frequency is 350 hertz around, and the transition bandwidth is about, well, from, let's see, how can I do this stuff in this, okay, maybe I'll just point it. So cutoff frequencies roughly there where we started at 350. Then we have the stop and start frequencies around 600. So now our transition bandwidth is 350 hertz. No, 250 hertz. If you want to go down by factor of 5, it means that you basically must go factor of 5 bigger on the on the minimum and maximum. So we, instead of from -4 to 4, we have -20 to 20. At the same time, we also have to change the window width. Okay, so there. Let's try that one. So, well, why I'm doing it? I just decided my target for transition bandwidth is 50 hertz, meaning that we need to go from -20 to 20 with n. Okay, so n equals from -20 to 20 and should improve the transition bandwidth by factor of 5. Oh, the command disappeared. It fit in on the, but anyways, it was just the, that's the command. There we go. And we have to calculate everything over. So impulse response is still that one. Then we have the triangular window, not any more from that one, but I think this would do the trick. Or does it? No, actually we have to start it from 21. Otherwise we are multiplying by 0 at the end. So it doesn't make any sense to add on either end any zeros. Looks like I'm missing something. Okay, I see. Wow. Sorry, it broke. Well, it happens on these, freeware programs. There's a new version of it, but I didn't. So I didn't take the new version, and of course I've lost everything here. Okay, but that wasn't too hard. So continue from the previous stuff. The indexes from minus 20 to 20. Then the FS was 2000, Fn was 1000, or actually Fs divided by 2. And then we have the HS was the sink. Fc divided by Fn times sink of n times Fc divided by Fn. Okay, and then we have, cutoff frequency, of course. Yeah, I need the cutoff frequency. Fc was 350 there. And what else? Then I have the TR function, which is 21 minus absolute value of NN divided by 21. And this was the place where it hangs up. That's fine. Welcome. You just missed the one thing. My octave actually crashed. Yeah. And I'll have the the video there. So okay, so the triangular window, and then just the frequency response. Yes, frequency response of HH1 1024 and sample rate like that. Then I'll wait for a while. Still waiting. Okay, so this starts to resemble a low-pass filter. So the cutoff rate, cutoff frequency inside of sink, not Fs but Fn, Nyquist rate. There, then I started with that filter and put there this triangular safe window to actually reduce a little bit of this the stop band attenuation. Well, it's actually like better now, so it's minus 40 there at the end, and then made the that actually was surprisingly well. So I estimated my transition bandwidth originally was 250, and now I actually put there 5 times more width for the filter. Uh, so basically now it's down to about 50 hertz. Yeah, so it works just fine. Excellent. How to improve it more? Use a real window, not triangular. Triangular window is the only good part of triangular window is it's fast to calculate even on a small processor. But on the other hand, those windows you would need only by selecting it, and then you usually also know the width of the window. So even for the small processors, you can always just have a lookout table, a constant lookout table for the coefficients. So let's take a quick look at what kind of windows we have. On FDA tool, you can actually find the windows that are available on MATLAB, but I always start with the help of Hamming window. Hamming, this actually gives also hints of the other window types, and that's how you use them. You just need to give the width of your filter, and this one returns a window function for it. So basically, let's see, at the end somewhere there's also help. Okay, does it have anything? No, it does not. Well, the MATLAB window functions usually tell you more about the types. But anyways, Hamming is one window. Then there's Blackman window, my personal favorite. Okay, Blackman window. Then there's the one Han window. And then there's also some window generators like Kaiser window. So that's a kind of nice tool, generic tool to produce basically any window. Then there is actually one optimized window available that was invention by one Finnish digital signal processor specialist in Tampere University of Technology in end of 1980s. Came up with a way to make an optimal window with basically controlling the flatness of the passband and the low band stop band attenuation. So that falls into category of the optimized methods. Okay, but anyways, those Hamming, Hanning, and there's also the Hanning. Okay, on Hanning and Hanning windows, Hamming, Hanning, Blackman, and other windows. On MATLAB, you get better help on different window types. On the exercise, you need to take few windows and compare which one will give you enough of the stop band attenuation. But I will just show you quickly how to actually do, for example, the Blackman window. BL. Blackman, oops, not Balkman, Blackman. Then just type the length of the impulse response. There, the sync. There we go. And then when you apply this one, for historic reasons, the filter coefficients are given as a one row vector, but these window functions are coming out of as a column vector. So basically you need to we need to the transpose this window generator window in order to multiply element by element. Otherwise, you will get some black text or red text. Okay, so BL equals the BL prime. Okay, the hyphen actually means transpose. Dot times HH. So the trick is transpose the window. On triangular, I didn't need to transpose it since I was generating myself. Okay, but then just for fun, figure, in my case, figure 2, frequency response of HHBL 1024 and FS. There we go. Ha! Now we are talking about a real low-pass filter compared to the, well, this triangular shape window. But of course, okay, there's always a cost. Whenever you have smoother window shape, you get the stop band attenuation goes better, but every time you are also widening the transmission bandwidth. So basically, to get the transmission bandwidth back, you need to then make the window wider. Okay, but we have the total control of everything here. So first, the cutoff frequencies is simply plugged into the sync function, and also here to for this the scaling factor to make it unity gate. Okay, then we take this smoother window shape to reduce the effect of this high frequency edges here, but that one gets you the better stop band attenuation with the cost of wider transmission bandwidth, and then finally you just basically scale your window size so that you will get the desired transmission bandwidth. So there's not much into it, and yeah, that's the result. That will be quite a nice filter already for the audio, for example. So you have something like 70 dB stop band attenuation, which is 12 bits, right? 12 bits. Signal to noise quantization noise ratio. Okay, good. Ha. And that was just a low pass filter. Haha. Next, let's go back to my slideshow. All right, where's my slideshow? There. So the window method. Start with an ideal low pass filter, and so on. So basically those 3 steps there. Sampling, convolution. There's some, and then there's some window shapes. Rectangular stop band attenuation is only something between 20 and 30 dB. Bartlett, Bartlett was the triangular window, what I made by, just by arithmetic. And then this Hamming, and Blackman windows. And then there are some of these generators like Kaiser window. And those are the window shapes. So basically they look a little bit like a bell curve, other than that triangular shape. And smoother you get, more you have a stop and attenuation, but then it also affects on the transmission bandwidth, which transition bandwidth can be then fixed by adding more values to your to the width of the filter. All right, next. That was the low pass filter. Done. I know how to do low pass filter now. But how about making a band pass filter? It's not that hard if you just basically do the modulation. Yeah. So why modulation? And what is modulation overall? Okay, you want this filter actually, for example, somewhere in here. Let me mark that as a modulation frequency. So this one actually will be transformed here, transformed. Like that. Which means that we take in frequency space and take the this frequency signal and modulate make the convolution in frequency space. So convolution in frequency space would transfer the properties of the filter right here. Well, don't forget it also transfers the second half here, minus FM. So, convolution in frequency space equals multiplication in time space. So if on the time space we have the system H of, again, when we have the time space, we have H of N, and then we have this frequency Fm. This actually single frequency would be sine or cosine. I prefer cosine actually. 2 pi Fm T or times sample time N times T. Yes, sample N times Ts there. Okay. So basically, this should give me modulated the new impulse response for the low pass filter with the width of 2 times the Fc. Half width is that one. It's quite obvious when you look at it. Remember, it's the both sides actually are transferred. Then it's divided into, meaning that actually you have to multiply this one by 2. Well, of course. Well, that's divided in 2 pieces. Okay, let's take a look at the MATLAB again to see if I did actually give you some false information. Wouldn't be the first time. Okay, so we have this nice filter with 350 hertz bandwidth, the cutoff frequency. So if I modulate that one, it's 700 hertz bandwidth. Okay, it barely fits into 1 kilohertz range, which is our 0 to Nyquist frequency. So for that one, I will just select the center frequency, which is the same as the modulation frequency at the middle. So Fn divided by 2, which is 500 hertz. Okay, not 5,000, but 500 hertz. Okay, and the middle of spectrum. There we go. Just to make the point. So basically then the HH band pass filter would be 2 times HH. I will take the Blackman windowed sync, modulate with cosine. I try to avoid the sine modulation because sine may have lots of zeros on it. At least at the middle there is 1 0. Okay. N times Fm divided by Fs. There we go. So that's the modulated low pass impulse response. Oh, okay, modulated low pass. Okay, and seeing is believing. All right, figure. How many figures? Okay, figure 3. Frequency response on HA's band pass 1024 points and Fs. Ta-da! Yep, band pass filter. Okay. So now you know how to make a low pass to band pass transformation. The easiest band pass transformation, a low pass to band pass transformation actually would be the next one. So, why did I actually close that? Let's put it back. Okay. Low pass to high pass. Exactly the same picture. Low pass to high pass. If you set the this modulation frequency same as the Nyquist frequency, you actually get a filter transformation from low pass to high pass, so that the high pass filter full bandwidth is the FC. Okay, there is a trick on the exercise. When you're doing the exercise, I'm actually defining the cutoff frequency of the high pass filter somewhere here. So first you need to think of what is the bandwidth of this high pass filter, so that you will design this low pass filter correspondingly. That doesn't look the same anyways. So Okay. Um, so this point here is actually that Fn minus Fc is the cutoff frequency. So to be careful when you're reading the this exercise. But anyways, now we have cosine of 2 pi. All right, so let's see. Cosine of 2 pi times Nyquist rate, which is Fs over 2, times n divided by Fs. Okay, Fs goes like that, which is cosine of n times pi, which is actually minus 1 to the power of n. Yeah. How come? Of course it is. It's obvious. Use the Euler's formula, for example. It will come out like that. So cosine of 0 pi is 1. Cosine of pi or any odd number n would be minus 1. 1 minus 1, 1 minus 1. Good. So again, let's take a closer look what it looks like. So the low pass to high pass transformation HP equals, we start from the change HHBL, low pass filter, and modify it with minus 1 to power of our index. It does not hurt to add some extra parentheses on this just in case. And then again, figure 4 high pass. That's nice. Okay. So it's let's take a quick look on what the low pass filter looks like. There you have the low pass filter. Not there. Low pass filter was here, and then we have the so what it does actually. Okay, another way of looking at this. This is the mirror image. How you get the mirror image on? Well, think of the z-plane. This is exactly the same thing as you will actually reverse the this real axis on the z-plane. If you are taking a look at the what is the difference between? Well, like we can actually do it since we have the technology. New figure with 5 z-plane of HHBL. Let's see what does it look like. It looks ugly. Yeah. Well, in MATLAB it might be actually different, but in my case it came out very ugly. So because of some reasons, this is almost singular point on those coefficients, meaning very close to 0. The filter probably would work better if you just mark that one 0. But anyway, so I can always just, do the axis for that one. Oops, axis minus 2, 2, minus 2, 2. Okay. Ah, nice. That's the zero pole plot for this filter. Does it tell you anything? Nah, not really. uh, the zero pole plots for these higher order the FIR filters are a little bit difficult to interpret. However, there are some principles. Basically, since we don't have the poles to compensate anything, the gain errors. Let's see. So what the only way we can actually do the those big attenuation on stop band is this one. It does not show that here though. There's something totally wrong with this picture. And how to this would end up giving me this kind of the uh, 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 the frequency response. How to then flatten this one with zeros, since all the poles are here. Only way is to put some zeros here, but not on the unit circle, but close to that point, so we can actually pull some frequencies down, like putting those here. Okay, but then basically it will go like that. But on the other hand, for the symmetricity, you also need the reciprocal pairs of those poles here, not the zeros. So that's why we have on the both sides, but there's also some computing accuracy issues on this one. This is already a 40th order filter. So MATLAB tries to solve the 40th order polynomial. 20 would be okay. 8 is piece of cake, but 40 requires a little bit more computing accuracy, I think. So one singular or nearly singular value actually messes up everything. Okay, but anyways, so I'm more or less happy when I just see this kind of pictures. Okay, so we have low pass, we have high pass, then we have the band pass filter. Then the only one missing is the, well, two of them are missing. How about band stop? Well, you see it here. Band stop is the combination of those, low pass and high pass. Just one warning, when you are adding these filters, you are also then adding these stop band properties, so you are pushing the stop band attenuation a little bit less. So 3 dB, you can expect to read 3 dB the less attenuation on stop band, but usually that's not the big deal. And of course, then if you have a different bandwidth here and here, then you need to, of course, design the high pass filter and low pass filter separately. As long as you keep the order number the same. If you want to really have the order number different, then basically you need to align the filters so that if the other one is wider, you'll basically add the filter 1 and filter 2 so that you are adding those on the same place. So what you are adding? Well, you are adding the impulse responses on time space. Okay, so that's how you match different length FIR filters. For example, to make the band stop filter. Then how about the multi-band filters? On the exercise, or one of the, was it today's exercise? Maybe it was how to make multi-band filters. Say typical multi-band filter is the tone control of auto radio. So there's the bass. Of course, on the bass you always go higher. And then you have the control on high frequencies, maybe a little bit higher than also on that one. The mid-range control basically is the volume control. So you have 3 bands. On digital filter from 0 to 200 hertz, from 200 to 2 kilohertz, from 2 kilohertz to, well, Nyquist rate. So you would need a low pass filter, band pass filter, and high pass filter. And then the implementation of that system is so that you simply have a system which calculates the new the impulse response by taking the B times the low pass impulse response plus M times the band pass response plus the H times the high pass impulse response, and use this impulse response in a system. There, you don't need to make the different bands, especially on the FIR filters. You don't need to band filter separately. You can just add the coefficients and have one filter with varying coefficients. Okay, good. Let me take a quick look at today's exercise to see did I cover enough of stuff. More theory. Click, click, click. Oops. No, what's there? Exercise template. All right. First, compare the amplitude response of the different window shapes. Actually, it's easier to compare those shapes if you set the cutoff frequency and use the sync there. But you can always just plot the frequency response of the window itself, nothing more than the window. Yeah. Well, using the window would be the ideal low-pass filter, meaning that your cutoff frequency is as small as possible. So it's basically just passing DC plus what the window actually allows. And then basically you need to design a, okay, use one of the, how to, what does it say? That's funny. Select one of the previous windows. How wide window do you need to take in order to change transient bandwidth by the factor of that? Design a low-pass filter. Okay, so that's where the fun begins. So those variables, just a reminder how all the filters in the world are designed. The low-pass filter design parameters. Magic. cannot be here, cannot be there either. Actually, that one can be here. Yeah. So passband ripple. So this is 0 dB. This is the ripple of what is the desired. If there's 0, then basically for 0 ripple systems you would have minus 3 dB as your cutoff the level. But for any other, then you would use the ripple for the cutoff frequency. So that point actually defines the cutoff rate. Okay, stop and start frequency, FS here. So basically any filter that fits this, for example, if it looks like that, that's okay. Or flat here, going like this. This is okay. Let's see. Of course. Well, whatever it does here, it will be okay. That won't be okay. There. So that box, just keep your frequency response inside of that area, then it will be okay. And those are the values. This defines the pass bandwidth. This is the stop. That point here defines the attenuation, stop band attenuation. Stop. The band in between is the transition bandwidth, or transition band. Good. Okay. For transforming the filter to, let's see, a transfer from previous filter with a center frequency. So, okay, so it's modulating the previous filter to be a band pass filter. Then design a high pass filter. Okay, now be careful and read it there. Cut-off frequency. So the design point for cut-off frequency on the high-pass filter is the physical frequency where the cut-off frequency resides. Okay. All right, verify your design from amplitude response graph. Okay, and then I have at some point I will change this one. This is a little bit hard, depending on the culture. How familiar are you with the different kind of languages spoken? Okay, I can give you a hint. There's a speech with a lot of noise, and the speech is not Finnish. It's some other language. What you need to do is to find first what is the voice and where what specular properties actually the voice has, and what might be the noise. When you make a spectrum analysis for the signal, it's quite obvious which part is the noise part. And then you design a filter such that you will get rid of the noise. At least, yeah. Enough of reducing the noise level so that you can hear the speech. And then you start guessing what language. When I took that sample from the, let's see, what is the pre-sound, I thought, okay, everybody will recognize this sample. It has been relatively hard. But for me, it was, okay, this is too easy. I have been keeping that one just for that reason. But okay, so, yeah. So spectrum analysis first, then design the filter to reduce the noise level. What else? Yeah, verify your design, and then filter the signal and try to hear what language the person is talking. You don't have to understand what they are talking, but just the language. This I think I have tomorrow, the multiband filter. Okay, good. So that's my part of the show today. So everything is now up to you to start working on the exercises. This is good stuff.